Hey everyone, thanks for joining us. My name is Akarsh, and I'm going to present with Jason RSR, Rapid Hitful Software Upgrades. So in this session, we are going to introduce what is RSR, why is it needed. Jason is then going to talk about Silicon One Express Boot implementation. We're going to discuss the different types of RSRs and then how it can be integrated in Sonic. So AI/ML workloads are very different from the traditional enterprise workloads. They're very sensitive to packet loss, and even a slight packet loss in the network can exponentially increase the training time, thereby wasting GPU cycles. Now, no matter how frequently or how slowly we upgrade softwares, there is an exigent need for the software upgrades to minimize packet loss and maximize fabric availability. So the natural solution is NSF, non-stop forwarding. So we leverage NSF to upgrade softwares in the network fabric because it's designed for zero packet loss and maximizing fabric availability. The problem is NSF is challenging. It's a complex problem space. It requires a lot of engineering effort to make sure that software releases are backward compatible and they're truly zero packet loss. Also, there's a problem that NSF can fail. Software releases cannot actually truly be backward compatible because you change data structures, DB schemas, etc. So what if NSF fails or you can't perform NSF? We fall back to cold reboot. Now imagine a torque connected to multiple GPUs across different racks. Now if you cold reboot that torque, you need to stop or pause training jobs across all those machines. You would need to drain that rack, cold reboot the switch, and then start training again. Now this is exponentially going to increase the job training time. And not just for NSF upgrades, so if NSF fails, we fall back to cold reboot, but even for switch repairs, we will need to cold reboot the switch again, significantly increasing the job training time. So I think there is a desire to actually have an alternative software upgrade mechanism that can be used as a fallback to NSF upgrades or even switch repairs for AI/ML workloads. So this problem can be solved through RSR. So what is RSR? It's rapid switch reboot. So it's a hybrid between NSF and cold reboot, but it's closer to NSF in the sense that there is a few hundred milliseconds or a sub-second traffic loss while upgrading the software. So like NSF, the data plane continues to forward traffic while the CPU is rebooted. The switch comes up to the new software. The previous intent or the new intent is pushed to the switch. Now that intent is actually cached in the SDK and it isn't forwarded to the hardware as yet. Once all intent has been reprogrammed, there is a signal called commit which tells the SDK to push all that intent into the hardware. So during that commit operation, the forwarding pipeline is stopped. All tables except the port tables are reset, and the SDK cache is pushed into the hardware. And finally, the pipeline is restarted. So the data plane loss is only during this commit operation, and the links stay up, very similar to NSF. So we can consider this as a near NSF upgrade with a few hundred milliseconds of traffic loss. Now, the efficiency of the commit operation really determines how much traffic loss happens during RSR. And as we optimize this commit operation, we can minimize traffic loss.
Yeah, so I'm going to drill a little bit down into the details of the implementation and talk a bit about how it compares with NSF. And we'll talk a little bit about NSF first and what some of the challenges are with NSF. So if you look on the left side there, you see like what is the standard warm boot NSF approach to restarting a switch or restarting an SDK or possibly an entire device in the kernel. Basically, you'll have some sort of configuration that's been played to the device by the version 1 of the SDK and possibly even a separate version 1 of the NOS. Okay, that's been pushed down. The SDK has, and the device itself has a bunch of state in it. The SDK has a bunch of state in it, potentially fairly complex state. And now the goal is to move to a newer software version. And the way this is typically done in warm boot NSF is this data is serialized somewhere to some persistent storage. It could be in a RAM disk if you're not rebooting the entire OS, but often it's actually to the SSD itself. And then it's the job of the second version of the software to basically load that state, restore it. Now keep in mind this is a separate software, so it needs to understand something that was produced by an older version of software. So if you think about any type of thing where you're writing new software, you might want to reorganize things, you might want to refactor things. So you have some challenges in terms of your software design there to make sure that you're able to be backwards compatible with that state. It restores it, and then it presents the same view to the upper layer that the first version provided. There's no changes in the configuration that actually happen as part of that state. So that presents two challenges. One challenge, of course, is this loading of this persistent state and the compatibility across various versions, especially if you want to jump versions or go backwards in versions and things like that. Oftentimes these are incremental or minor releases. And the second is that it's presented a single view to the outside world. So an example is after a warm boot NSF, you might present to the upper layer the exact same ACL tables that the first version had. So taking a single feature example there. So you've presented a single set of ACL tables the first version had. The second version of the NOS itself or the configuration might want to reconfigure that. They might want to recarve the tables. They want to add something to the key and remove something from the key. Well, now it's the NOS's job to basically say, let's do a reconciliation and make changes. And if those aren't done correctly, the OS itself could introduce packet loss and misforwarding and things like that at that layer. So it becomes very challenging even at the OS level to kind of deal with that configuration change. So the idea here with an express boot is let's focus very, very heavily on simplicity. Let's take a fresh config, potentially at the OS level and certainly at the SDK level as an option here, and then take that and then push that to the device after the reboot. So you're probably looking at that and saying, well, that looks like cold boot to me. Well, the difference is that we do it really, really fast. And the question is, how do you do it fast? Because ultimately, when Sonic, for example, is pushing config, it doesn't push config in nearly enough time. Like a standard fast boot reconfiguration is allowed to go up to 20-something seconds. And we're looking at something with some different goals there. So the goals we're looking at is several. The first goal is that this should be stateless. And stateless is really the key to simplicity in this mode. We don't want anything checkpointed and saved and carried over from one version to the other that could potentially break or create incompatibility. And the idea there is that this should allow for any kind of SDK upgrade and even downgrade. And we'll talk, and Akarsh will talk also about the software and Sonic level coming up in a second, also to allow even the Sonic level to be able to make changes or whatever NOS is applying there. The goal is to keep the traffic interruption to as little as absolutely possible. In many cases under 50 milliseconds, potentially between 50 to 100 milliseconds at very high scales if there's a lot of data to push. And the idea there is that the ports need to stay up and the protocols that are transiting across the device need to stay up. You shouldn't be seeing TCP sessions time out. You shouldn't be seeing anything else like that happen. It should look like potentially a congestion event or some small blip in the network, but everything should be staying up. And the idea here is to find this sweet spot between a warm boot, which is hitless, but has this high complexity to it, and something that's like a true cold boot, which has this huge impact and have this impact that doesn't break SLAs and things like that. As I mentioned before, NOS configuration changes can be especially challenging in a warm boot situation because, for example, taking that ACL table redefinition case I mentioned before, typical way the NOS would deal with it is create a new table, switch everything else to use it, delete the old table if, for example, the keys and result fields had changed. But that could run into resource constraints and things like that. Maybe there isn't enough space. You really want to use all your space in the device. You don't want to have to reserve space because you're going to be doing these warm boots. And even if you did reserve space, did you really do enough? Big testing challenges there. And also, you may want to actually redefine the entire data plane behavior via the P4 program at runtime. You might want to introduce some big feature, move things and lookups from one stage to another within the device and make significant changes, but you still want to do that in a nearly hitless way. And so now you have an option to even push a completely data path redefinition. With warm boot, with programmability and warm boot, you still can push your P4 changes all the way up to production time, so you don't need to wait for the new ASIC like you would with a hardwired fixed pipeline. But now with this mode, you can even do that very quickly, even after in production at runtime with a minimal impact, and not waiting for some sort of cold boot maintenance window that probably comes very, very infrequently and is undesirable in many cases to have at all. So if you look at what's actually happening under the hood, in the sequence for the express boot is that Sonic version 1 in this case, or it could be any NOS, but in this case it's Sonic, will be running over the SDK Sci version 1, and everything's happening very, very happy on the left side there. So what actually happens, never mind. So what actually happens there is the Sonic version 1 will say, okay, SDK shut down, I'm going to shut down, but leave the device in a continuously forwarding state. So right now it's still forwarding packets in the V1 data path. Okay. What happens next is the new version of the software comes back up. This might involve a kernel reload. It might involve just the Sonic reload. It might involve just SWSS and syncd reload. It could be any level of reload that's happening. The new version comes up, and what will happen now is rather than playing the config of the device, at a very, very low level, at the memory and register level, everything is just being pushed and saved in a cache. So all the configs are still going through. They're still reporting resource failures if you're doing something wrong. There's still, all of the protections in there are there of the API. But it's basically pushing everything at the very low level, memory and register level, into the device. And at some point, it gets a signal from the upper layer saying, I'm done. I pushed that configuration that I want. It might have been the same configuration as before. It might be a completely new configuration. But it's pushed that into this device cache through the SDK APIs. And then there's this optimize and stage phase that happens. Typically, this involves reading back some values from the device. Keep in mind, the V1 data path is still forwarding. Nothing's being dropped. Everything's happy. All the packets are still flowing. And it's basically staging everything to be able to push into the device as absolutely fast as possible. And then, at that point, we enter the critical section. And this is where you want to minimize packet loss, but you will have some packet loss. And we pause the pipeline. And the reason to pause the pipeline is because the actual memory registers and writes to the device and memory writes to the device actually happen much more efficiently and quickly when there isn't packet flowing. And that's because typically memory accesses by the CPU need to wait for bubbles in those memories because they're being used in a packet per clock forwarding system that's actually consuming a lot of those memory bandwidth. So we pause the pipeline here, push that data to the device on the order of milliseconds, and then immediately do a sequence to resume the traffic under the new configuration. And now, from that point onward, the traffic is flowing again, and the new Sonic version is able to push regular APIs through the SDK, now down to the new version of the data path, potentially. Okay.
So there are different types of RSRs. In this presentation, we're going to talk about two of them, local and remote. So local RSR is when intent reprogramming and the commit signal are actually coming from the switch itself. So they're triggered internally from the switch. So for example, switch wakes up, reads config DB, app DB, replays all that intent to syncd, and syncd passes it to Sci through the SDK, and that gets cached in the SDK. Once the intent reprogramming is complete, the commit signal is sent by SWSS itself. At this point, the pipeline is stopped, the SDK cache is DMA'd into the hardware, and the pipeline is restarted. So as Jason mentioned earlier, this operation to the external world is completely transparent and looks like just a blip, a few 100 milliseconds of traffic loss. And the external world is really transparent of the RSR itself. So the use cases of this type of RSR are, Jason talked about upgrading the ASIC P4 program. So you don't need to do a cold reboot, just upgrade it through RSR. Another thing that we can do is to recover the switches in case of SDK failures. So if you minimize the amount of checkpointing done by the SDK, you can actually recover from a lot of the SDK failures in both non-NSF and NSF scenarios. You can also perform any version to any version SDK upgrades depending upon the amount of information that you have checkpointed. So like Jason mentioned, Express Boot does not checkpoint anything. So it is a truly any version to any version upgrade. And you can also perform backward incompatible SDK upgrades. remote RSR is different in the sense that there needs to be an external entity that needs to orchestrate this RSR process. So the intent reprogramming and the commit operation are actually coordinated by this, for example, an external controller. So the external controller, for example, triggers the reboot. It needs to be aware that the reboot is complete. Then it pushes the new intent onto the switch, knows that the intent has been reprogrammed or has been programmed and saved in the SDK cache, and then it's going to push the commit signal so that all that SDK cache can be pushed in the hardware. So this remote RSR is actually a superset of local RSR, where you can perform ASIC P4 program changes, but now you can also recover from general software failures, because there is minimal amount of checkpointing done by the software itself. Now, not just SDK failures, but software failures can also be recovered. This can be used to perform software upgrades from any version to any version, and also backward and compatible upgrades. Jason talked about ACL redefinition. So ACL recarving can be done through remote RSR, where the new ACL definition is pushed and the commit is performed. So there is existing support for RSR in Sonic. Sonic supports local RSR. So what Sonic proposes is that all layers in the switch stack perform NSF except for syncd, which will perform RSR. The way it's done today is there's a platform script, warm reboot, fast reboot, which during shutdown sends a custom notification to syncd. Syncd, depending on the notification type, performs NSF shutdown or RSR shutdown. And therefore, you see these, one vendor can perform NSF SCI APIs and the other vendor can call RSR SCI APIs. So if you look at the current implementation, there are custom notifications all across the switch stack. So from platform scripts to syncd to vendor SCI implementation. Similarly, during boot up, there's a custom boot up type that's passed to syncd, and based on that, it performs RSR boot up. The proposal is to unify these custom implementations into a common boot type like RSR. So RSR is a concept. It doesn't necessarily have to send custom notifications. By unifying the RSR, we can actually localize the vendor-specific code inside SCI itself, where it's actually supposed to lie. So during shutdown, we can send an RSR notification. syncd performs an RSR shutdown and call the common RSR SCI API, and then the vendor can decide whether it needs to perform an NSF shutdown or an RSR shutdown. Similarly, during boot up, a common RSR boot type can be passed to syncd, and the vendor can perform RSR boot up. So the previous slide talked about how it can be integrated with the existing Sonic approach. A couple of years back, Bhagat and I talked about reboot backend and a new shutdown orchestration framework for NSF. The same orchestration framework can be used for RSR as well. So for that, we're going to introduce a new reboot type called RSR that gets pushed through GNOI to a front end like UMF, which gets passed to the reboot backend, and the reboot backend starts the RSR shutdown, where it first sends a freeze notification so that the switch becomes quiescent. All applications stop generating new intents. That is followed by a checkpoint notification, which all applications interpret as a checkpointing to save their internal states, whereas syncd performs an RSR shutdown, and therefore it calls the RSR SCI API, and the vendor can implement it based whatever they want, NSF shutdown, RSR shutdown. During boot up, it's pretty similar. Boot type is RSR passed to syncd. It starts caching requests. Call to action. Let's unify RSR in Sonic. Let's try to leverage it for NSF failures, for recovery from switch failures. There's a workgroup called the System Orchestration Workgroup, where we previously upstreamed the NSF orchestration design, and we're going to discuss more about it, collaborate about RSR in that working group. Thank you.
Any questions for the speakers?
I have two questions. One is I see the slide saying about a less than 15 millisecond drop, and the other you mentioned a couple of hundred. Am I missing something?
So that depends on the vendor implementation of RSR.
Okay.
So let's say vendor X has implemented in a way where there is a higher drop, and it also depends on the scale of the flows being programmed.
Okay.
So it's
okay. So there's like a minimum 15 millisecond all the way to a couple hundred millisecond possible, right? Depending on the scale.
that's vendor specific, but
Okay.
Jason can talk about how Cisco has done it.
Yeah. So the biggest table that tends to affect that is the IPv4, IPv6 routing table, the LPM table. With typical data center type routing scale, we see around the 50 millisecond and measure that, and we're working to bring that even further down. So there's still room for optimization there. If you're completely filling it up, we're getting closer to a max of around 100 millisecond. But again, there's work to continue to bring that number down.
Okay, the second question related, does it, if there's a congestion or not, matters or not on the switch being rebooted or being RSR? Let's say PFC is going on, there's a queue build up. Does it matter or not when you talk about this loss window?
So I can speak to our implementation. So it doesn't matter. What's happening is during the shutdown procedure, of course, everything will continue to operate normally. So PFC will be honored, buffer management will be honored, congestion, ECN, everything in the data path continues to work normally. Now, when it comes back and starts that sequence, basically it's going to shut down the incoming packets, and then it's going to push the new configuration. After it finishes pushing that new configuration, that resume process is basically what we call a soft reset of the device. So it's a similar technique that's also can be used, for example, to recover from a stuck pipeline or things like that, where it's basically resetting via specific sequences and register rights basically in the device, basically telling every block, just start over from scratch. So basically everything that's been queued up in the buffers is gone. Everything in the traffic management, scheduled credits, everything's kind of reset almost to like an original state. So anything that's been queued up will be flushed at that point.
Sorry, a little bit more. Do you have to drain the packets before you reset?
You do not need to drain the packets. They will happen as part of that reset operation. They'll effectively be as though the queues have been reset to zero.
Just flash.
Yeah.
Okay, thank you.
Quick one, Akash. Actually, maybe two related questions. One is that there's a lot of data structures, hardware on this kind of data path that can be incrementally and without disruption changed, right? Do you have to, in this process, do you have to stop traffic even for those, just for simplicity, or you just disrupt traffic for the specific memories that cause packet disruption? A quick example is like changing a interface usually is done incrementally during runtime, or installing a new route is done incrementally during runtime. We don't stop traffic for those, right? Why would we stop traffic here? And the other one is that how does this make the upward complexity of NSFs, like in the stack, things like reconciliation, health check, and those kind of things easier? Does it make them any simpler?
Yeah, so I could take the first question. So typically, if you are looking for a modification or upgrade or something that can be done without disruption, you typically would do that in the NSF model. So you would go down an NSF type of restart and have a software version that's compatible using NSF and do an NSF style upgrade into that. Where you would go and choose to do an RSR type restart, at least if it's just from the point of view of the SDK and the data path, is when you are making changes that would force disruption. Like let's say you've decided to make a major data path change in the P4 program that moves one table from one place to another, or you're doing like a redefinition of keys or something else like that. That's kind of a major disruptive change that's going to affect basically cause a disruption in any case. For small things like a feature configuration change or something's writing something a little bit different to register, usually what you would do is have just the v2 version load NSF if you wanted NSF, and then deal with that compatibility difference between the two versions and say, okay, the old version did things this way. I know I'm loading from the old version. I'm doing things this way. Let me make the change in the hardware to do things the way that the v2 version would do. Of course, you can choose to do an RSR just for simplicity purposes for any type of version conversion, including ones that would normally be NSF compatible.
Quickly just adding to that. So RSR is not replacing NSF. So AI/ML workloads cannot have so much packet loss throughout the network. So this should be infrequent. Secondly, yes, it would make the complexity less, but again, you cannot replace NSF. That complexity will still be there unless someone just makes these training jobs more robust to traffic loss.
So if every vendor implements RSR, so does it mean that cold boot is not needed anymore? Or what are the limitations of RSR?
I think in my opinion, cold boot should be used as the last resort. Where RSR doesn't work, let's say the vendor implemented checkpointing of ports because they don't want to touch it during boot up. And there's a failure related to ports, and now you can't recover it through RSR. Right, so in that case, you'll have to perform a full reinitialization.